Thank you very much for the invitation to speak here. So today I want to talk about extension counts in random graphs, and all this is joint work with Matas Šileikis from Prague. So what is the natural context here? So subgraph counts in the random graph GNP is a very classical topic. So we're interested in understanding what can we, for example, say about the number of triangles in a random graph. And the first question you would want to ask is the existence threshold. So in other words, for which edge probabilities P is it true that with high probability, with probability tending to 1 as n tends to infinity, we can find at least one copy in our random graph. So we want to find at least one triangle. And once we know that there's at least one triangle or one copy of H, we can now start asking other questions. Particularly, we might be interested in the concentration question. So we are interested in what ensures that the number of copies of H is close to the expected value with high probability. And it turns out for this answer, the classical first and second moment will allow you to answer this concentration question. In fact, just the second moment. So these are very well understood questions. And over time, people have asked more and more interesting questions, like what is the distribution of the number of copies of H? Or what can we say about the probability that your random graph has too few or too many copies of some given graph H? What is the probability of that? Instead of asking a more detailed question about this classical subgraph counts topic, what I instead want to do is I want to look at a variation or an extension of these classical subgraph counts, which I want to call here rooted subgraph counts. And intuitively, we're all familiar with this concept. So here in the classical subgraph counts, we're asking how many triangles does our random graph contain? So it's like a global question. How many copies do we have globally? And rooted subgraph counts is some kind of local version of this. We're interested in what can we say about the number of triangles that contain a given vertex? What can we say about the number of paths of a certain length that go through two particular vertices? That's the kind of objects we're interested in. And when we ask the concentration question, the natural variant is we're interested in what conditions ensure that, for example, at every vertex, we have approximately the same degree, which should be close to the expected value. Or what conditions on P ensure that every vertex is contained in roughly the same number of triangles? Or similarly, that every pair of vertices is contained in roughly the same number of paths of length 4. So this is the kind of question we're interested in. What conditions ensure that all these kind of quantities here have the correct counts? So I'll try to define on the next slide exactly what rooted subgraph counts are, but I hope this sort of gives you some intuition about the kind of objects and the kind of questions we're looking at. So once we see this quantity, which is really an extension of the classical subgraph counts, we should ask, so maybe why should we care? What is the motivation actually for looking into this? And here, so on the one hand, I think this is really an extremely natural generalization of the classical subgraph count topic. So given that we have now all this amazing technology to analyze random graphs, we understand very, very many quantities extremely well. This is something that honestly we should be able to understand, right? The second motivation is that these rooted subgraph counts, this is something that actually appears quite a lot in many proofs inside the proof arguments. And the one very classical topic where these kind of objects are important is the study of 0-1 laws in random graphs. Another area where or another thing where it really shows up a lot also is in many probabilistic proofs where at some point in the proof, you might want to say, oh, I'm looking at a certain set of vertices and I want to make sure that this set of vertices is not contained in too many cliques or too many subgraphs of a certain type. This is something that can be very useful inside proofs. And this is exactly also a variant of this rooted subgraph count question. And this really goes through the analysis of many probabilistic models. Even if you analyze like various random graph processes, it turns out that in many cases, somehow these rooted subgraph counts are something that you're interested in. So it's really widely used, appears in a range of applications. The third motivation, which is how I originally arrived here at studying these rooted subgraph counts, is that they provide a convenient test bed for studying various concentration inequalities. Because one approach for studying such kind of questions here, like every vertex has roughly the same degree of every vertex, roughly the same number of triangles, is that you can, for example, just do some union bound argument where you take a union bound over all vertices, and then you ask yourselves, okay, what's the probability that your particular vertex has the wrong degree, in the sense that it's not very close to the expected value. So this would be a classical, you do a union bound argument over all vertices, and then in this case, a Chernoff bound to analyze the degrees. Okay, and the interesting thing here is that for these rooted subgraph counts, it becomes a little bit more challenging to understand here the concentration inequality part, because you cannot just anymore apply the standard Chernoff bounds, but you need to use something more complicated, because the variables you're interested in are no longer independent. Okay, I hope this gives you some idea where this kind of topic fits in. It's a generalization of these classical subgraph counts, and one way to think about it is classically we study global properties, and what we're doing here is local properties or a local statistic. I also want to mention, if there are any questions and so on, please ask them during the talk immediately. So let me say a few words about rooted subgraph counts or rooted graphs. So let me quickly define this. And so let's maybe look at a small example. So here we're going to look at some two vertices, v1, v2. And they will be the root of some graph H, maybe in this case, this graph here. Okay, so the entire thing here is the graph H, and I think of these two vertices here as the designated root of this graph. So in this talk, all roots will always be independent sets. Okay, and so this naturally generalizes to other situations that I mentioned. For example, also in the case of a degree, this just corresponds to an edge where you root at one of the two endpoints, and so on and so forth. Okay, so in general, we have here some graph H and some designated root. So what do we consider now as rooted subgraph counts? So the idea is that we're going to fix ourselves some set of vertices inside the random graph GNP, and then we're going to count the number of H copies in our random graph GNP where the vertices of this particular set I correspond to the vertices here of the designated root in our graph H. Okay, so you can think of it as the number of H copies where the vertices of the set I that you fix get mapped to R. And because of this property, one can think of this roughly as the number of extensions of I, of the set I, to a copy of H in our random graph GNP. Okay. So this is the natural extension of this notion that we discussed, like degrees, where you think about it's the number of edges containing a given vertex. Okay. I think it's best to understand this through a few examples. Here I prepared some rooted graphs as an example. So here I have this this cherry, and I want to root it here at these two vertices. Then what we're counting here is just the number of these cherries where the endpoints get mapped to these vertices. So that's just the codegree of these two particular vertices, W1, W2. then here's the example that we've already seen a few times. So here I have a triangle and I want to root it at one particular vertex. Then this extension counts just counts the number of triangles containing W. And you can do it similarly for other structures. Like here, this is a path that we root at its endpoints. So this is just the number of paths of length 4 containing W1, W2. Note that here it's really important that we decide on which root vertices we choose, because the thing that we would count is very different if we, for example, make these two vertices here the root instead of these two here, okay? So it's important which designated vertices we choose. Maybe to also give an extreme example is when the root is actually empty. Okay, so we're looking at some rooted graph where the root set we pick is just the empty set. Well, then what happens is that this extension count just is degenerate. It's just degenerate in the sense that we're just copying the number of H copies in the entire graph. Okay, so if the root is empty, we just reduce to standard H copies. Okay, so we have rooted copy. We count these extension counts of some particular set I to a copy of H. And what we're going to be interested in is to show that this quantity behaves roughly the same for all possible choices of this I. Okay. Just to maybe get used to this random variable, let's quickly try to calculate what the expected value here actually is. Okay. So note that by symmetry, it does not matter which particular set I you're choosing here. For every possible choice I, the expected value of this random variable will be the same in the random graph. And so what is the expected value? Well, it's very similar to normal subgraph counts. So what's happening here is that, well, we fixed the vertices of the root. And so now we need to choose a certain number of vertices outside. So the number of vertices outside is, in this case, the number of vertices of the entire graph minus the number of vertices of the root. And then we need to put down the remaining edges, which each of them is present independently of probability T. Okay, note that here, because we assume that our root is an independent set, that's why we don't need to subtract anything off here. Okay, so this is this notion of rooted subgraph counts, or we typically call it extension counts for this reason. Okay, so as I mentioned, the goal is that we want to basically ensure that for all possible choices here of this set of root vertices I, we get the same number of extensions to H. Okay, this is the goal. So intuitively it says, specializing to some examples, every vertex has roughly the same degree. Every vertex is roughly contained the same number of triangles. Every pair of vertices is contained in the same number of paths. So this is a very classical question that I think the original study of these kind of questions goes back to the study of logic in random graphs. There's some early results, I think, by Scheller and Spencer. And then in 1989, Spencer wrote some nice paper on this topic where he basically gave some very good sufficient conditions which ensure that you get this kind of a concentration result. And let me tell you here in one important special case how this looks like. So here we want to say, so we given some rooted graph, and the important the important case here is when the graph is so-called strictly balanced. So let me for the moment not say exactly what it is, but intuitively, the examples that we've seen, they're strictly balanced, and strictly balanced means kind of the graph is nice, it's not ugly. So let this be a strictly balanced graph, strictly balanced rooted graph. And then what the statement is, he says, okay, basically you want to show that it's in 1 plus minus epsilon around the expected value. So in other words, for any epsilon in 0, 1, say, he proved that there is a constant which depends on all these quantities, on epsilon and the graph that we're rooting at, such that what? Well, we want to show this, that all extensions are fine. So we're interested in the probability that no matter which choice of I we're looking at, the number of counts is always close to the expected value. So we get here that this is 1 plus minus the expected value. Okay, so this here is a slight abuse of notation, this 1 plus minus. But what it means here is that this random variable lies in the is at least 1 minus epsilon times this value and at most 1 plus epsilon times this value here. And he proved that this goes to 1 if the expected value is sufficiently large. Okay, so again, what is the statement? We fix some rooted graph, which is nice, in this case strictly balanced. And he showed that if the expected value is sufficiently large compared to log n, then no matter at which set I you're looking at, you always have the same number of extensions to H in this rooted sense. Okay, and this kind of statement maybe we're intuitively kind of familiar with here, that here there's some log n appearing. This is something that's very typical for coupon collector type problems, where you need to make sure that everything is hit or everything is okay. Another where you see log n behavior is very classical, just look at the degrees of a random graph, right? We want to ensure that at every vertex we have roughly the same degree. Well, our experience tells us, if we do this kind of union bound plus Chernoff argument, that then we need that at every vertex the expected degree is sufficiently large compared to log n in order to make this statement true. And one can actually show that if the expected value is smaller than that, then you can actually find some vertex where it will be violated. Okay, so this is kind of a very natural condition here. And so the question that Joe Spencer raised in this question is, in some sense, is this sufficient condition that he got, right? Because this just tells us, if this is true, that we get this one statement, is this sufficient condition best possible? So is this a sufficient condition best possible? Okay, so that's the question he raised there. In particular, he remarked in this context that his proof shows, as you would expect, that k tends to infinity as epsilon goes to 0. Okay, so the smaller, the better concentration you want, the larger you need to make this constant. Okay, so in some sense, what he's really asking for is kind of trying to figure out what is the right dependence here of k on epsilon. That's really his question. Okay. Let me just say one or two things about this notion of strictly balanced. Okay, so this is really, in some sense, an extension of the definitions that we're familiar with from normal subgraph counts. And in normal subgraph counts, what kind of matters is that somehow the densest spot of your graph H matters, so where the ratio of edges to vertices is highest. And there's some analogous definition you can make for rooted subgraph counts, just that in this case, you need to take the ratio of the number of edges divided not by the number of vertices, but by the number of non-root vertices. Okay, so, then the graph H is strictly balanced here for rooted subgraph counts if the graph H itself maximizes this notion of density. But the precise definition for the purpose of this talk is not so important. The main message is that nice graphs are strictly balanced. We have seen some examples. Let me just maybe draw a few more. So here, if we take any path and we root it down here, this will be strictly balanced. Same if we do this for cycles. Rooted at one vertex, this will be strictly balanced. If we root a clique at one vertex, it will be strictly balanced, and so on and so forth. So the question is now, how does a non-example look like? Something that's not strictly balanced. Well, maybe one of the simplest examples you can imagine is that you have some long path. So you root at this vertex, you have some very, very long path here. And then what you do here is you put something very dense, in this case a clique, all the way at the end of this path. And then so somehow intuitively, the fact that there's this clique over here is much more important than whether there's this path here. And so this is something which would be not strictly balanced, okay? Okay. So, so we were interested in answering this question of Spencer. And so how does our answer look like? So here, again, we want to look at some rooted graph. So in this case, we can, let's say, look at strictly balanced. And in this case, for the statement I'm writing down, we need one more definition. Let me just say it. So in this case, it should be grounded. So what does grounded mean? Grounded is intuitively, it just excludes some degenerate cases. So if you have the graph is not grounded if you have a root, but there's no edge connecting the root with the remainder. So I don't know, something like this. If this is the root, and here you have some cycle, well, this would be a rooted graph in our sense. But I hope we all agree that this is, in some sense, a very degenerate situation where the root vertex is not connected with the remainder. That's degenerate, and as we'll also point out in a moment, the behavior there is different. Okay, so our result says strictly balanced.
Ungrounded case, how can we imagine it?
Okay, I intended to put it down here, but the answer is that in this special case for strictly balanced graphs, the ungrounded case is basically just counting copies of the thing that's outside. So in this case, the intuition is that, well, look, we're counting these kind of structures, a vertex plus in this case the C4, but intuitively there will not be too many copies of C4 sitting on one vertex. So the total number of copies of rooted copies of this type is approximately equal just to the total number of C4s in our random graph. Okay. So we can handle that, but the reason is that in this ungrounded case, you do not need this logarithmic factor here. That's why I need to exclude it from our theorem, because there actually you don't need this logarithmic factor.
Yeah, so ungrounded means that you just count copies that do not meet these vertices that are roots. And there is also a question from Dmitry Zakharov in chat. He asks, okay, as far as I understand about the result of Spencer, is it true or not for not strictly balanced graphs?
Okay, so I stated this result here for strictly balanced rooted graphs, because there his result is the easiest to state and the closest to being tight. He has also a sufficient condition in the general case, which, as I'll mention later, is not best possible. The answer there this looks a little bit more complicated. So basically, what he does is he kind of reduces the general case to the strictly balanced case, in the sense that he says, okay, if certain rooted graphs all have the same counts. For example, one vertex is contained the same number of triangles. Every 3 vertices are contained, I don't know, in the correct number of copies of some other graph. If all such intermediate guys, all these extensions are correct, then you get overall the correct number of extensions. So he has results that also sufficient conditions, but those are less. They're very useful, but they're less tight and harder to state than here the strictly balanced case. Or maybe I misunderstood the question. Let me quickly see how to get to the chat here. So it may happen that for.
Yeah, I think that the last message is a way of an answer on this question also.
Yeah, so I'll say something a little bit later about this in talk in one particular example, but this is exactly the reason why one has this distinction between strictly balanced and not strictly balanced. That if it's strictly balanced and the expected value here tends to infinity, then it's also true for all sub extensions in some sense. That's kind of the reason why strictly balanced is nice. Somehow the entire graph is the thing that we really should care about. The subgraphs play a less important role, but it's right. In general, we have to take all possible subgraphs into account, and I'll say a few more words about that. Okay, so let me try to state our result. So basically, we want to refine this result. So we look at a routed graph which is strictly balanced and grounded. So here, what we can show is, so there's a bunch of constants, alpha, small c, big C, such that, well, this is not so important, but let me still write it down. So we can allow epsilon to go to 0 at some small rate. It's maybe not the most important part here of the statement, but the main statement is now that we get some threshold phenomena. So we're interested again, the probability that all these extension counts are correct. Now we don't just want a one statement, but we want two different statements. So we want that in one regime, we get this probability goes to 0, in the other it goes to 1. And what is the condition that we have here? The condition that we prove in this case is that the correct criterion should depend on epsilon squared times the expected value. And well, based on Spencer's result, you might guess that you get a 0 statement that if this is at most a small constant times log n, and you get the 1 statement if this is a big constant times log n. Okay, so intuitively, what this is saying is that instead of just looking at the expected value, we should look at epsilon squared times the expected value. And if this quantity is sufficiently smaller than log n, then we get a 0 statement. That means we find some set I, which extends to the wrong number of copies of H. Whereas if this same quantity is just a little bit larger, some big constant times log n, then this is no longer possible. Then we know that with probability tending to 1 as n tends to infinity, all these sets I extend to the correct number of copies. Okay, so this is related to the usual notion of thresholds. Gives, say, threshold for the concentration of these extension counts. Just that here, instead of just looking at the edge probability P, we also take into account this epsilon. And let me also just point out that, so this really answers this Spencer's question. So if we go back one slide and see what was there going on. Remember, so he proved that if the expected value is at least some big constant times log n, you get the 1 statement. He asked, okay, is the sufficient condition best possible? In other words, what is the dependence on k? And so basically what we showed here is that k should be of order epsilon to the -2. Okay, so this is one other way to interpret our result, that the correct choice here of the constant k would be epsilon to the -2. Okay, so you might ask, okay, or let me point this out directly here. What is really the main contribution here of our results? So the main contribution is really the 0 statement, which was missing in previous work, right? So previous work was focusing on sufficient conditions, but there was no 0 statement. Okay, so we need to show, in other words, how can you show that you have at least one set I where this condition is violated. And a third remark I want to make concerns here the ungrounded case, which I promised to talk about a little bit. And there, the intuition is that it's roughly the number of copies of H without R. So let's again, otherwise, look at the example I gave earlier. So the example would be, again, something degenerate. You have something like this and maybe a triangle. And the intuition is that, yeah, this is formally a rooted rooted copy, and you can even check that this under the definition that I gave you, that this is strictly balanced. This might be on first sight a little confusing, that something that's not connected is strictly balanced, but take my word for it, this will be strictly balanced under the definition for rooted subgraph counts. But intuitively, it's quite clear that the number of such extensions is basically the total number of triangles in the entire random graph. The idea being that, well, the number of triangles sitting here on this particular vertex is should be quite small compared to the total number of copies. So here, based on this, the answer changes. So here we get a 0 and a 1 statement under different conditions. So here we need to basically get rid of the log. So here we get a 0 statement, not if this is less or equal than a constant times log n, but if this tends to 0. And we get the 1 statement if this tends to infinity. Okay, so these two cases really behave qualitatively differently. And this grounded case, where there's at least one edge from the root to non-roots, that's really the interesting case. This case is not so interesting. Okay, are there any questions at this point?
I'm sorry, I don't understand 0 statement.
Okay, so the 0 statement, let's specialize, for example, to the situation where we look at this example here. Okay, we're looking at the number of triangles contained in one vertex. So what the 0 statement means is that I can find one vertex where the number of triangles that contain that particular vertex is either less or equal than 1 minus epsilon times the expected value, or larger than 1 plus epsilon times the expected value. So that's what I mean by that you have the wrong subgraph counts, that you're relatively far away from the expected value by this factor of at least 1 plus epsilon, or at most 1 minus epsilon. Okay, and the fact that here we don't get these extra logarithmic terms, that exactly comes from the fact that here, basically what you're doing is you're basically counting, in this example here, the total number of triangles in your random graph up to some small error term. So that's why we don't need this extra logarithmic term up here, which intuitively comes from the fact that at some point you want to do some kind of union bound argument over all possible, for example, vertices. And in this case, you just don't need to do that. Okay. More questions before I move on?
I'm sorry, in the Spencer result, epsilon.
So here he considers a fixed epsilon, yes.
Okay.
And so his constant also depends on epsilon, but that's implicit or hidden in his argument. So basically, we're trying to understand here how is the dependence on epsilon, or what is the correct dependence on epsilon. Okay, let me otherwise move on. Say one or two things about the proof. So we want to show exactly what was just asked. What do we need to show for the 0 statement? So we need to show that there's some let's again just work with a triangle example. We need to find one vertex which sits in the wrong number of triangles. Okay. And so whenever in random graph theory we need to show that something bad exists, the first thing that comes to mind is that we want to use the second moment method. So want to use second moment method. And so basically the simplest thing we can do is just counting the number of bad I. Okay, so we calculate the expectation and the variance of this, and then hope for the best that we can push this through. So if you try to do that, you run into two conceptual difficulties. So one is, let's just look at the first moment. So typically calculating the expected value is the easier part of the job usually. But here we already run into something that's a little bit tricky for two reasons. On the one hand, we need to calculate this probability here, the probability that you have the wrong number of extension counts. We need to estimate this basically up to a 1 plus it log of 1 factor if we want to apply the first and second moment method, the second moment method. We need to know this probability very, very precisely. And the difficulty is that this probability in the range we're looking at will be quite small. It will be, say, polynomial small, or maybe even smaller, maybe even exponentially small. In that range, it's usually hard to estimate things up to 1 plus it log of 1. Okay, so that's one thing which is maybe a little bit different from usual applications. And it also contains some, in some sense, difficult problem, as it contains this, what some people call this infamous upper tail problem. So what that basically is related to is that what's really hidden here are two different questions, right? One is the question that your count is too small. We need to estimate the lower tail of this random variable, or that you have too many, the count is too high, which corresponds to the upper tail. And whereas the lower tail of this quantity can be very well controlled using, say, Janssen's inequality, for the upper tail typically is much harder and much less well understood. One of the reasons is that while the lower tail behaves more in some normal-like fashion, the upper tail, some more complications can happen, because intuitively in your graph can contain some very dense structure, some very small, very dense structure, which generates you a lot of these extension counts. And this can cause some headaches, some technical difficulties here. Okay, so again, the main point is just estimating this probability is really tricky. So even if you manage to overcome this first difficulty, the second challenge is that somehow the second moment that we're doing here is not really of the normal kind. So when we think about usually of second moment arguments, typically what we have in mind is something like, oh, let's count, for example, the number of triangles in a random graph, where you look at certain indicators, and each indicator corresponds automatically to some local event. It corresponds to the event, oh, these three edges of my triangle are there. And then you calculate the covariance between different indicators. What's a little bit tricky here is that this is not really a local event, because the question whether you have too many or too few copies or extensions, that kind of depends on a lot of edges of your random graph, right? Because if you have, say, too few copies, it tells you, yeah, a bunch of these copies of H, they cannot be there because I have too few copies. Or if I have too many, it says, okay, a bunch of these copies must be there, so a lot of edges must be there. So this is something just to keep in mind that one needs to be a little bit careful about, that it depends not just on a constant number of edges, but depends potentially on many edges. Many edges of the graph. And so we need to be a little careful about that. Okay, so how do we overcome it in this particular case? So the idea here is that our goal is just to show that there's one bad such bad root. There's one vertex which has the wrong number of triangle counts. But we have the freedom of deciding how we want to prove that. Nobody forces us to just count the number of bad eyes. We can do whatever we want as long as what we show implies that. And so the idea here is that in some sense, we will just cook up some event that's a little better behaved than just this event that you have too many or too few copies. in some sense, we're going to specify exactly how we want to achieve this event. I'm going to tell you exactly how you achieve this event, and that gives us more structure to work with, okay? So, so in other words, we're going to show that some event holds with probability 10 to 1, which just implies this event. And so here, one way to express this is that with high probability, there is I, which attains this due to some very special reason. Okay, in the range where we need to prove things, we basically show that this is attained in some very special way. So say 1 plus epsilon times the expected number of many copies due to extensions, which in this case, this works, which are vertex disjoint outside I. Okay, so to look at this triangle example, or say counting number of K4s in here, you would instead look at the event which looks somehow like this. You want to make sure that all the copies here that you get, they look somehow like this. So here the key point is that these copies here, all these copies here, they're vertex disjoint. Okay, so again, we just specify one particular way we want to get too many copies in this case. And we do it using an event that has a lot of structure that we can estimate things. Because, you know, if things are vertex disjoint outside I, you can imagine that you can calculate such probabilities very precisely because you know exactly what is the situation that must happen